first announcement. So, a week from today, so I will be at the coast. Be passing through there on the way to New Orleans. So I'll be running the show from there. We have two students who are enrolled in the coast section. So we'd like to combine and have the same in-person teaching experience that the handful of you have here in Hattiesburg. That will be able to, and I'll try to make one or two additional appearances before the semester is over. So that'll be my first one. Okay, now, so continuing with Bessel functions. Not much to say about them. Okay, now, I've mentioned one example, and we're going to see get into this example in more detail later on. If you are solving, for instance, the Laplace equation on a disk, or more generally in the cylindrical coordinates, then you have to express the Laplacian operator in whatever coordinate system you're using. And so when you do that, the example I'll show you later is for cylindrical coordinates. You perform what's called separation of variables, which I'll illustrate toward the end. You have an ODE for each one of your variables in cylindrical coordinates, and one of those turns out to be a form of Bessel's equation. So solutions would be related to Bessel functions. And what ends up happening is your solution to your PDE you want to be able to express as a series expansion, so coefficients times Bessel functions. So when you're doing that, as we've seen from in the beginning of the course, where you're writing a function f of x as in terms of an infinite expansion, infinite series of functions, is you want those functions to be at least orthogonal, if not orthonormal. That way, we can compute all the coefficients of a series expansion independently of one another. So, what we'd like is to have Bessel functions be orthogonal in some sense, so we can do exactly that. But this is the application to be able to express a generic function as a series expansion involving Bessel functions to be able to compute the coefficients. So what we have here is the Bessel equation, although so really the solutions of this ODE are these Bessel functions of the first kind. So and notice the order of a Bessel function is the Greek letter nu. And nu is not assumed to be an integer, but it is assumed to be greater than or equal to -1. So what this equation is saying is that J nu of K rho is a solution of this ODE, which is the Bessel equation. Now, what I'm going to do is rephrase this equation as describing an eigenvalue problem. So all I've done is taken this term and moved it over to the other side, and then divided through by rho squared. And this is what we get. That we have a differential operator, linear differential operator, applied to the Bessel function, is equal to constant k squared times the Bessel function. So J nu of k rho is an eigenfunction of this differential operator L, and the eigenvalue is whatever number is multiplying the Bessel function on this side, k squared. As we've seen, if you have a set of functions that are eigenfunctions of a differential operator, if the differential operator is self-adjoint, then the eigenfunctions are orthogonal. If it is not self-adjoint, then you can find a wave function. They can be orthogonal with respect to that wave function. What do we have in this case? This operator is not self-adjoint, because remember, to check for self-adjointness, you take the coefficient of your second derivative term, which is p naught, the first derivative term, which is p1. P1 has to be the derivative. Wait, this is written totally wrong. Prime should be on the other side. P1 needs to be equal to P naught prime. Whoops. Okay. This is one of those, you know what I meant kind of deals. Okay. So, point is, it's not self-adjoint. So, therefore, we need a wave function. And the formula for wave function was established some time ago. We're calling it here. It's 1 over p naught times e to the integral of p1 over p naught. So we fill in all of that. And what we get, well, and thankfully everything works out pretty nicely, is we get minus rho for wave function. Oh, I should point out that when it comes to wave functions, the constant factor is not relevant. You can use a different constant factor if you like. It's customary, for instance, to make a wave function positive. Okay. Now, this is something I've established in a previous section. Now, this statement is very general, where we have U is an eigenfunction of some linear differential operator, and so is V. Corresponding eigenvalues are lambda U and lambda V. And WX is whatever wave function that your operator needs to be made self-adjoint. So, so what was worked out previously was that this integral turns out to be equal to this. It turns out to be something that can be integrated exactly. So we have b conjugate u prime minus b conjugate prime u times wp naught. Evaluate limits a and b, whatever a and b may be. This for whatever scalar product you're using. Now, in this case, we have w is minus rho, and then p naught is equal to minus 1. So this part here, wp naught, that just turns out to be equal to rho. So if I fill in what the eigenfunctions are for our specific case of the Bessel equation, first of all, we're going to use limits 0 and a for some a. So since this part here turns out to be equal to rho, and rho is being evaluated at 0 and a, the lower limit term will not give us anything because it's 0. Whereas for the upper limit term, we're going to have all of this stuff multiplied by value of rho at a, so we have a. So only the upper limit term contributes anything. So WP naught, that leads to this A right here. For the rest of it, the role of, okay, make sure I have my piece straight. Okay, so the role of U, I'm going to write this in here. U of rho equal to J nu of K prime rho and V of rho J nu of just K rho. The eigenvalue corresponding to, let me go off here, make sure about this. Okay. Yeah, I do have these backwards. Because here we have lambda nu minus lambda v. So lambda u is k squared, lambda v is k prime squared. All right. Still feel like my sign is off. Sorry, I need to make sure we get this right. What that is, I did look this over earlier today, and everything seemed fine then. Okay. Okay, I see what happened. So here, when the wave function was worked out, here's minus rho, and I mentioned earlier that constant factors can be modified if need be, because we like wave functions to be positive. Okay. So we'll just make W go rho. Okay. So with that in mind, W times P naught will be minus rho. Okay. And now everything will work. Yeah, so the sign was just out of place. Okay. So what we have here is how this works out. Here we have U B prime. Because we're taking the derivative of this with respect to rho, and by chain rule, we get a factor of K prime introduced. And then here we have B with U prime, and everything evaluated at rho equal to A. And then this part, the difference of eigenvalues, we divide by that gets moved down here. So by applying this relationship with these particulars, this is what we get for the integral. So what I want to make clear here is, here we have VU prime minus V prime U. On the one hand, we have the terms in the opposite order down up in here in the numerator. The ordering here, lambda U minus lambda V, is the same as what we have here. But because W P naught is equal to minus rho, that's why the expression is taller. I'm remembering, since it was 9 years ago when these first version of these notes were presented, and now I'm kind of remembering how it was often an exercise in seeing what's done in a book. It's like, okay, there's no way on earth that any student's going to see how they get this. So I'm going to have to untangle that ball of yarn and put it in notes. Okay. All right. Now, we want these functions for k and k prime distinct to be orthogonal. That means we want this whole expression to be 0. So that would be achieved if both Ka and K prime A turned out to be roots of the Bessel function J nu. That's what we'll do. We're going to require that for each eigenvalue, remember the eigenvalue is k squared. So corresponding to each eigenvalue, square root of the eigenvalue times the upper limit of our domain must be 0 of J nu. So what we end up doing is, right, because recall in the previous expression we have k rho and k prime rho. So I want to describe the zeros of J nu by alpha nu J. So the first index is the order of the Bessel function you're taking the zeros of. The second index, J, is indexing those zeros, because each Bessel function has infinitely many zeros. It oscillates. So this is how we identify all those zeros. So since Ka and K prime A is equal to alpha nu J for some index J, that means that K is equal to the 0 divided by A. And all that's multiplied by rho. So here are our orthogonal functions. So J nu of root over A times rho. So that set of functions is orthogonal. Any questions about? Now, you recall from multivariable calculus, aka Cal 4, that if you're evaluating an integral and you want to put in polar coordinates, so instead of integrating with respect to x and y, integrating with respect to d rho d theta, you need to put in an extra factor of rho or r, whatever your radial variable is, for a change of coordinates from Cartesian to polar. And notice we have that factor right here. We have a factor of rho. That comes from the wave function. So what we could say is Bessel functions are orthogonal with respect to this wave function, or another way to look at it is they're orthogonal with respect to the unweighted scalar product over a disk, not circle, disk of radius a, because if you're integrating over a disk of radius a, then you're integrating from 0 to a d rho, and then from 0 to pi in your 0 to 2 pi in your angular variable, often referred to as theta. I'm going to be using phi later on. Maybe this is this thing. This is like to use different variables for everything. Just to confuse us.
I mean, you confuse me too, so.
Okay. Oh yeah, I forgot we had a hybrid in the room here. Yeah, it's especially interesting when you have both math and physics students in the class. But yeah, like the spherical coordinates are different. Oh.
Yeah.
Okay. So, so when you print polar coordinates, then this integral falls out naturally for the radial part. And these eigenfunctions are independent of whatever angle, theta or phi anyway. So we have that helpful perspective. Now, we keep in mind our original goal, that is to be able to expand functions in a series of Bessel functions. We need to know how this should be normalized, so we can get an orthonormal set of Bessel functions. That would be helpful. So so aside from our functionality, we need to know if I is equal to j, what does the integral turn out to be? Because if we go back to the original result, which is reproduced down here, we have these values k and k prime. If I set k equal to k prime, we'd have a 0 over 0 situation. That's an indeterminate form. So what we need to do is take the limit of that as k prime approaches k using Multitask Rule. So what happens when we take the derivative of this expression, top and bottom separately, with respect to k prime? But we also have to keep in mind that k times a is equal to a 0 of a Bessel function. Okay, so what ends up happening? We set ka equal to a 0 of a Bessel function. That gets plugged in here. So this whole term is going to go away because that's going to be 0. Okay, this part will not be 0 because we still have k prime, it's approaching k. Right. So now we focus on this term right here. So we have k times a, and then we have all of this as is, but ka is also a 0 Bessel function. And then what we have here, we take the derivative of this with respect to k prime, we're going to get minus 2k prime. So up here we have k, down here we have minus 2k prime, but k prime is approaching k. So in the limit as k prime approaches k, this will cancel out with the derivative of this. Okay, the minus will cancel with this minus. The 2 is going to stick around. Okay. Now, this part doesn't depend on k prime. It stays the same. So I still need to take the derivative of this whole the numerator with respect to k prime, but the only place where k prime shows up is right here. So what am I going to get? I'm going to get j nu prime of k prime a, and then by chain rule, I'm going to have another factor of a. So you know what? I'm going to, as I've done many times before, put in an intermediate step, because what's written here is I've filled in Ka equal to alpha nu I over root. I've not yet actually applied L'Hopital's rule to this. Okay. I want to show that a little more clearly. So downstairs I have minus 2k prime. Upstairs we have k8. So then we have j2 prime k prime a times a. So now you can see how this ends up becoming this. So we have two of these a's. K and k prime cancel because k prime is approaching k. The minuses cancel. Still have a 2 hanging out there. Now we have these two derivatives evaluated at different points. But k prime a is approaching ka, which is this. So that's why in the limit, both derivatives of Bessel functions are evaluated at the same point, alpha nu I. So that is what the integral ends up as. Any questions about how we got here? Considering that L'Hopital's rule is a concept that we teach in Cal 1, but the other school I taught in Cal 2. Having taught both lower level and upper level classes, so recurring theme I see is that between the big difference between problems in lower level versus upper level classes is that the problems in upper level classes are simply more cluttered. Like something like this. Like when you're first learning L'Hopital's rule, like in Cal 1, the problems apply to the relatively simple functions. Everything's nice and sanitized. So then it comes something like this, and it's like, ugh. But what you're doing is still a lower level concept, but in a scary setting. What?
Proves you know it.
Yes, yeah. And that's what professors always hope for. We're often disappointed, but but once in a while.
You can't tell it that.
Yeah. Okay. But we're not done with this question. We're going to write this a little differently. Because we can write this without being a derivative. That'd be nice. And it turns out we can do that because this is one of the several recurrence relations involving Bessel functions that was given earlier. It was not derived because you got to do that for homework. So what I do with this is I'm going to choose the minus sign, and I'm going to perform an index shift. So where we see nu, that'll become nu plus 1. So then nu minus 1 on the right side will become just nu. So this recurrence relation, by choosing the minus sign, is equivalent to this one. But then I'm going to set x equal to a 0 of j nu. So if I plug that in here, here, and here, well, x is therefore 0 of j nu. So that term's gone. So j nu prime of alpha nu I is the same as j nu plus 1, no derivative at that point. And the other is a minus, but the whole thing gets squared. So this is what we'll use to help us normalize these Bessel functions. Now what we can say is this integral, okay, equal to 0 if I is not equal to j, and if I does equal j, it's Now, ready to work with expansions. This is what we came here for. So we have some function f of rho. We want to express it as an expansion in these Bessel functions and find these coefficients, c nu j. So the coefficients will depend not just on the index of the summation, but also the order of Bessel function you're using. So I can use a Bessel function of whatever order I like, as long as u is greater than -1. But each one of these Bessel functions is evaluated at a different point using a different zero of that Bessel function. One thing I'm wondering about, and I don't know offhand, so I'll have to check. Because previously we had a requirement that nu is greater or equal to -1. Okay, for this to be a solution of this. Whereas down here, we have nu strictly greater than -1. I don't know offhand what goes wrong if I let nu be equal to -1. So if I remember, I'll have to check. Now, I could just let that slide and don't might not notice, but you do have equalized students now and then. So. Okay. So how do we get these coefficients? Now, when you have functions that are orthogonal, but not orthonormal, this is the standard formula that your coefficient of your expansion is a scalar product of your orthogonal function with the function you're trying to expand, that's always the numerator, and then the denominator is scalar product of that same orthogonal function with itself. So this is no different than what we saw at the beginning of the semester. Now, this denominator is worked out up here. So we go ahead and fill that in, so the reciprocal of it. And then this is scalar product with the appropriate weight function of your Bessel function with the function you're expanding. So there you have it. That's the formula for all the coefficients. Self-Adjointness integrals, which is probably never nasty, but that's what software is for. So we realize our goal, how to expand a function. So if you're solving, for example, let's see. So if I set rho equal to a in here, so what's left is you're evaluating Bessel function when it's 0, so that's going to be 0. So at rho equal to a, this whole expansion will turn out to be 0. But the idea is you have a function f of rho that's defined, for instance, maybe on a disk of radius a. And it's only dependent on the radial variables. It's not dependent on your angular variable of theta or phi. This is how you can describe it. Now, I should mention that so what we did here to ensure orthogonality, we wanted this to be 0. And we got that by requiring that Ka, K prime A were different zeros of the Bessel function. However, and that's good for what's called Dirichlet boundary condition, where you're requiring that a certain function is equal to 0. But what if you want the derivative to be equal to 0? That's called a Neumann boundary condition. So I could have also imposed a requirement that Ka, K prime A were equal to zeros of the derivative. And we also would have gotten orthogonality that way. So different set of orthogonal functions. So certain details would be different. But the point is we can choose either kind of boundary condition. So in this case, Ka is equal to beta nu j, where it's equal to j0 of the that way that whole expression would turn out to be 0. Questions up to this point? Now, one use of these kind of expansions is to solve a PDE. And this is a PDE that I've mentioned as an example. So, positive equation in cylinder. So A is the radius of the cylinder, and we have our domain in Z goes from 0 to H. So it's a cylinder of height H. So this is a positive equation. Velocity is equal to 0. And we're going to impose these boundary conditions. So at the outer boundary of the cylinder, the solution will be 0. So we're using phi as the angular variable. And then at the lower end of the cylinder, which corresponds to Z equals 0, will also require a solution of 0. But then at the top end, Z equal H will require that our solution is equal to some given function f of rho and phi. That's referred to as a potential function. We need to express the Laplacian in cylindrical coordinates, and we have that here. As a chain rule exercise, we'll do. Some of you saw that last semester. Well, not for cylindrical or for polar coordinates. So it's not 2/3 of the job. Right, the interesting part of it. Okay. Now, how we solve a PDE like this using separation of variables, what we do is we assume the solution has this form. It's a function of rho times a function of phi times a function of z. And what you do is you substitute this form for v in the PDE. So what you end up doing is each one of these differentiation operators is taking derivative of only one of these at a time. So the derivatives work out pretty nicely. And we also then will divide by v, and for notational convenience, we're also going to actually divide by v over rho squared. So this is what we get. Because when you divide by v, a lot of cancellation happens. So we have this part involving derivatives with respect to rho, this term involving derivatives with respect to phi, this term involving derivatives with respect to z. Now, since this is a cylinder, we need the phi part to be 2 pi periodic. In other words, it should be, so phi of phi should be, I guess capital Phi, little phi. I don't make up the conventions. This should be a linear combination of a sine and cosine. That's 2 pi periodic. So we specify that second derivative of capital Phi with respect to little phi is equal to minus m squared big phi, where m is an integer. And that would have this as a solution, which is a linear combination of a cosine and a sine. So this right here, this second derivative, we can replace that with minus m squared phi, and we get 2 pi periodicity. Then we're going to require that this second derivative is equal to fancy L squared times capital Z. And we know how to solve this also. So when you don't have a minus, instead of e to the I m phi, we don't have the I. So e to the plus or minus LZ. And we don't know what L is yet. What we can do is keep in mind that the Z part, when little z is equal to 0, if you look at our boundary conditions, it has to be 0. So what we do is we describe our solution to be linear combinations of e to the LZ and e to the minus LZ. We subtract them, so really we can describe capital Z as a hyperbolic sine. So the reason for that is if I substitute little z equals 0 in here, I'll get 0. Therefore, that boundary, so this boundary condition will automatically be satisfied. So taking care of one of our 3 boundary conditions, we've ensured periodicity in the phi variable, the angular variable. So we're getting there. Now, with these substitutions, this one taken into account, this is what we have now. So now we have an ODE, where the only variable for which we haven't solved yet is capital P. But this is a Bessel equation, order M. And these are the solutions. Where this L comes from here. We still don't know what L is. To specify L, we need to require that when we set rho equal to A, that this is 0. And that's because of this boundary condition right here, first one. So like we saw before, L times A needs to be a 0 of Bessel function of order M. So that means that L must be this. So it's equal to a 0 of Jm divided by A. And now we have all the pieces. Because, I have the wrong L in here. The number's wrong font. Okay, that should be fancy L. All right, so now we have all the pieces. Bessel function for the rho part. Complex exponential 2 pi periodic function for a phi part, and then hyperbolic sine for the z part. So this function here, this capital V, that is a solution of our original PDE of Laplace's equation. Now, Laplace's equation is linear, so any linear combination of solutions is also a solution. Now, what have we satisfied so far? We have satisfied this boundary condition and this boundary condition, but we haven't accounted for this one yet. So this is the only thing left. So now what I'm going to do is take a linear combination of these solutions with coefficients C, M, J. M going from minus infinity to infinity, and J going from 1 to infinity. J is indexing the zeros of the Bessel function Jm. M is the frequencies for the complex exponential that we have here. So what we have here, this is our solution, except that we've substituted H in for Z right here. So if we set Z equal to H, result must be equal to F of rho phi. That's the remaining boundary condition. So now we have this series expansion. All that's left is we need to find the coefficients. because we set c equal to h, this is a constant. That won't pose us any problem. The Bessel functions are already been established to be orthogonal. So we did our much of our early part of the class. And these functions, these complex exponentials, also orthogonal. We have this orthogonality relation for that. So by using both orthogonality relations, so what we do is we take the scalar product of Jm times e to the im phi. So this whole part that I've highlighted here, we take a scalar product of that with f. That's why, keep in mind, we have to take a scalar product of two functions. One of them has to be conjugated. That's what leads to the minus right here. So e to the im phi gets conjugated with e to the minus m phi. So scalar product with wave function, our basis function, series expansion, with f, and we have to divide by the scalar product of this function with itself. And then we also have this constant to account for. So this constant, it just heads down to the denominator. And then we have, from a scalar product of a Bessel function with itself, that's what leads to this Bessel function squared, and we have a squared, and we also get a 2 up in the numerator. But then we also have to divide by the scalar product of this complex exponential with itself, which gives us 2 pi. So when we put a 2 pi down here, the 2 down here with 2 pi cancels with the 2 that this expression brought up here. Now, keep in mind the scalar product establishing orthogonality of the Bessel function, that was just with respect to rho on the interval 0 to a. The scalar product involving the complex exponentials was with respect to phi on the interval 0 to pi. So we have, so really, this double integral here is, we have 2 scalar products going on at once. Unfortunately, we cannot separate it into a product of 2 integrals because we have f that depends on both variables, so that has to stay inside both. Okay. And those are our coefficients. So once we compute these, we have our solution. Okay, so I'll just make a copy of this. Don't change very much. So it'd be b of rho by z is equal to all this, where z right there. So that's the solution of the Laplace equation with cylinder with that kind of boundary condition. Certain variations with its possible changes of boundary conditions. Like if this had been partial derivative with respect to rho being equal to 0 at a, that's a Neumann boundary condition. Then I would have the zeros of Jm prime right here. Another possible change is if this boundary condition at z equals 0 had been derivative v with respect to z at z equals 0 to 0, that also is a Neumann boundary condition. So then I would have had some expression here involving cosh rather than sich. Okay. Questions about all the crap that happened here? That was a lot. Those of you who took 417, 517 last semester would recognize the general separation of variables process, but those examples tend to do with sines and cosines. Well, we did Laplace equations toward the end of the semester. But that was a different domain, not involving Bessel functions. And then, are you taking it next semester? PDE 417? Yes. Okay, so that's why you'll see that. So you're seeing the more cluttered example of separation of variables up front. Yeah. Yeah, you're seeing everything wrong order. Okay. Okay. Do we have any homework questions? Peanut gallery. And some here in this room. Well, okay then.